Hey guys, what's up? For today's video, we will be solving welded connection no, under eccentric loading uh, in steel design. Okay, so we have our problem. The plate is connected to the column using 8 mm fillet welds. Okay, so the required are the shear stress due to the load alone, shear stress due to moment, and the maximum shear stress. Okay, so here's our figure now. So there is a 140 kilonewton load applied at a distance of 300. That's 425 from the of the center of gravity of the welded connection. Okay, so this is our center. Oops. Okay, so let's go jump to our solution now for number one. So number one, shear stress due to the load alone. We have our formula FVP. This is shear stress due to load, and we have our P, no, P direct divided by the area. Okay, for steel design, FVP, or for welded connection, no, P direct is equals to this one is the P total divided by the total length of the welded part, and our area is T sub E. Okay, so to further derive no T sub E, if this is our plates, okay, so and this is our welded part, no, so this is our welded part, so the thickness no that is given is this one. Okay, and what we want here is this depth no from the outer part of the welded area, so this one, that's the weld no this area. Okay, and this is the thickness that we want, which is that is the T sub E, in which that is sine 45 of the thickness. Okay, so in short, that's 0.707 times T. Okay, so that this value will be used no in our computation of the FVP. So we can now solve and substitute value. So FVP is equals to the P total, that's 140 kilonewton, convert no raised to 10 times 10 raised to cube, divided by the total area of the welded part, so that's 250 plus another 250, that's 500 millimeter, all right, divided by the area. Okay, so this is the unit area per length, so that's 0.707 times 8. Okay, so we have our shear stress due to load alone, that's 49.5 MPa. All right, so we have our answer now for number one. Okay, so number two, the required is the shear stress due to the moment. Okay, so we are looking for the shear stress due to the moment, so we can use no, this formula. Fv is equals to moment times the radius or a radial length no, over j, and multiply it by the area. All right, so that's times the area. Okay, so we have our m is equals to p times e, in which our p is 140 times the eccentricity no, so that's 300 plus 125 millimeters, so that's 425 millimeter or 0.425 mm, which is equals to 59.5. Okay, 59.5 kilonewton meter. We have our rho. So from the figure, this is our rho no, it is the farthest part of the welded connection, in which this one the most in which critical shear occurs no, and this is our x value, and y, in which y is 100 millimeter and x is that's 125 millimeter. All right, so we can solve for rho, so that's 100 squared plus 125 squared no, which will equal to, so that's square root of 25,625. All right, and our j, oh, and our area no, area is simply T sub 8, in which it will be 0.707 times 8. Okay, and our polar moment of inertia, so that's I sub x plus I sub y. But then we have no inertia no, along the y. Okay, so this will be 0 for this one. So what we have is the I sub x. Okay, so this will be j. Our j will be due to the small, relatively small width, no. So we will neglect no and set as 1, and what we will consider is the length. So that's L cube no, L cube over 12 plus 0 for this one no, transfer formula. there is no x, so that's 0 plus the y. Our y is 100, and since we already assume now that this is 1, so for the distance now we will assume that uh, it is directly the distance, the half distance of the member, okay, to the centroid of the welded part now. So this one, so that's 100, okay, 100 squared, and then times the area L, no, and multiply this by 2 since there are two welded part now, times 2. Okay, so we can now solve for J. So that's 250 cube divided by 12 plus 100 squared times 250. So multiply it by 2. So we have our answer, 7.604 times 10 to the 6th power. Okay, so we can now substitute values. Our FV will be moment. Our moment is 59.5, no, times 10 to the 6. Convert it to Newton millimeter. Multiply by the rho. So that's square root of 25,625. All right, divided by the area. So that's 0.707 times 8. This is due to torsion, FVT, times the 7.604 times 10 to the 6th, no, in which will yield to, that's 221.46 MPa. Oh, sorry. So this will be MPa. So this will be our answer, no, for number 2. Okay, so for number 3, no, so the required is the maximum shear stress. Okay, so our maximum shear stress, no, FV max is the total shear stress, which is R over the T sub E, in which R is equals to the square root of P dx plus P Tx squared plus P dy plus P Ty. So this is just simply adding, no, the forces induced by each stress, no, okay, in a Pythagorean formula. Alright, so we can solve P dx equals to 0. So since there is no force now along the horizontal direction, and P dy as, so that's 140 times 10 cube divided by 500. Okay, so this will result to 280. Next is our PTX, right? Okay, so in order to get the PTX, no, so that's just the area, or FVT times the area, in which we will get the component for the X component for this shear stress. So that's area, it's 0.707 times 8 millimeter thickness times the component, no, so that's 221.46 MPa times, so that's 100 over the square root of 26. So this should be 25.625. All right, 25,625. Right, so we have values for that one, and for PTY, no, so that's 0.707 times 8 times 221.46 times the RX, no, so that's 125 divided by the square root of 25,625, right? So this should be the RY, no, 100, and this should be the RX. Okay, so we can now calculate. So this PTX will be 782.5, right? And this one 978.098, or that's 1. 978.1, right? So we can now calculate the total reaction. R is the square root of PTX, so that's 782.5 squared plus PDY, so that's 280 plus 978.1 squared, no? So our R here is, that's 1481.6, no? So we can now calculate for FV max or FB total or max, no, equals to R 1481.6 divided by 0.707 times 8. So we have our value 261.95 MPa. So this will be our final answer for number 3. Okay, so I hope this video helps you guys. So thank you so much for watching.